think we have mentioned high gain control, but haven't finished yet. And I will introduce another two controllers, which is high frequency controllers and the adaptive control. So we haven't finished the high gain control, and some students have questions about the control structure. So here in the control, in the high gain or robust control, we have two terms. One is minus kx and the other one is VR. And I say VR is a robust term. And if you notice that VR is basically minus k2x, which is similar to this minus kx structure, right? So basically they are the same. Okay, so you can say my control is minus k and k2 x. Okay, it's the same. Okay, you can define this as k1. The reason that I decompose this control into two terms is I want you to see how k2 can change some convergence properties. I will continue from there. We say vita is nd as long as this condition holds. It cannot always hold, right? As long as x first go to the zero or trivial solution, right? As this x becomes smaller and smaller, this condition will break. So the takeaway is the larger the uncertainty on the parameters, the larger it will be error, right? Which can be observed from this C. Remember that this C is the upper bound of the uncertainty. This is the upper bound of the unknown parameter here. So if you have a larger unknown which reflect on a larger C, then given the same control gain, right? A larger C will result in a larger X, absolute value of X, which X you can interpret as UUB ball. So if you start from here, okay, it will decrease until some value. Okay, it's always decrease as long as this condition holds, right? Because when it holds, vita will be negative, which means it's always decreasing, right? When this condition breaks, and that happens at this point, right, at some x, which is non-zero, right, and it stopped decreasing. It's hard to see from here, it stopped decreasing. Anyway, remember this, okay? How will you find the UUB bound? This is called the UUB bound. Eventually that V will converge to some constant value, okay? It's not hard to imagine from here, right? And you will understand why it converges to a constant in a few seconds. So starting from here, let's take the analysis of x dot again, okay? So you have k minus kx squared minus k2x squared. We keep the first term, right? And we say that if second term will be negative if the condition holds. If this condition holds, vita will be negative, right? Which is this, okay? Now we do it in another approach. Let's try another approach. And we want to find the ultimate bounded. What's the ultimate bound? Which is this, okay? What's the value of this is, okay? Or in other words, what's the when vita will be zero, okay? So let's try complete the square. In Chinese, it's called 配方法. So let's focus on these two terms. So these two terms can be considered as minus ax squared plus bx, okay? A and b are some constants, in which case a is k2, b is theta sine squared, okay? And it's equal to the right hand side here. using complete square 配方法，对吧？ So in the right hand side of the equation, you have two terms. The first term is always negative or equal to 0, right? The first term here is minus a something squared. So it's a non-negative function, right? Right. And the second term is some positive constant, okay? You substitute back to here, which give you what? Now you see that this remains the same. This term is negative. So that you can by dropping these terms, you can drop this term out because this term can be bounded by 0, right? Bounded by 0, which means bounded by nothing, right? So you drop these terms. Okay, you drop these terms, and you keep these two terms, and it becomes the upper bound, right? 对不对？负的东西可以被零 upper bound 嘛？负的东西它永远小于零嘛 ？Right？ So here is equal sign, right? We want to upper bound this. Let's do it term by term, right? This can be upper bound or equal to this, all right? And this is the same. Right, the same, right? So it still holds, right? The inequality still holds. And how about this? It's always upper bounded by 0, right? 对吧？一个负的东西。So you can drop it. You can say 0, which is you just drop it, which is this. Okay, right? 没问题。So now we say this is C. Okay, another C. No. So and this is 1, right? Can be upper bounded by 1. Sine power to the 4th, upper bounded by 1. And theta squared can be upper bounded by c squared, right? 对吧? So this can upper bound this. Okay? Now it's clear, right? The only variable here, everything here is constant other than the x, right? So now, when in the worst case, because it's inequality, the worst case for v dot to be 0 is this summation to be 0, right? Okay. For v dot is upper bounded by okay. And let's say the worst case is equal to 0, okay? We want to find that when this guy equal to 0 means this guy stop to decrease and remain a constant, right? Right? So let this to be 0. You can compute the only variable x, which is what? Right? And you can compute x, absolute value of x. And what does this x means? It means when v remain constant, the corresponding x. Corresponding x norm. X norm we know is already decreased, right? And remain a constant. And this is that. The result is it will be for sure, right? And the answer is how close your state will converge to. And the answer is this. Okay. 透过条件，你可以让它收敛到多靠近于原点，就是靠这个来回答。So if you from here, you can see if I increase k or k2, right? This value will decrease, which means you can converge more close to the origin, right? Or your error can be decreased by increasing the gains. So let's get back, make a quick conclusion. So what's the question? Question is this: given some dynamics with unknown parameter theta, I know the upper bound of this unknown parameter, right? I design a robust controller trying to stabilize the system, and I know that it's impossible to get a syntactic stability. The best I can get is the UUB, right? Which means that x cannot converge to 0, but it can converge close to 0. How close? By given the control gain that you design, right? That's the answer you're trying to get, right? So this is what you have, okay? System controllers, the upper bound of the uncertainties. And in the end, the answer is by doing some analysis, okay? Remember this control structure, use a high gain control, and you can, after a sequence of analysis, which is completely square, find the worst case, and you can compute that the x will eventually converge to this value. Okay, and by increasing the control gains, you can make x arbitrarily close to the origin. Remember what you have in your hand, and the tool is the upper of analysis, stability analysis. Okay, here's the trick: you can use complete the squares to take care of the upper bound, the worst case. Here is you have problems, right? You don't know theta, whether it's positive or negative. So it is hard to define C. But here C is just a positive constant, right? And you let the analysis take care of the rest, right? This term will be used during the analysis, which comes into play here, right? You upper bound from here to here, you take care of the worst case, so you put the absolute value here, right? Such that a positive number can upper bound which could be positive or negative, right? So no matter it's positive, no matter the value, the product value here is, it always can upper bound this, right? 对吧? And it's another equality here, and C come into play to upper bound this. So every term, every upper bound is very solid, right? And from here you can start to apply complete squares. Okay, here is not complete square. Here is another approach. Okay, but it's basically the same as complete square, similar. Okay. Here we don't put the absolute value to upper bound these products because we're trying to use complete square, right? 能懂吗? But both cases take care of the worst case. Here, whenever you see equal sign, there is no worst case. The worst case happens when there is an inequality, right? Which means you apply upper bound. The upper bound from here to here is I drop this negative term, which can be upper bound by 0. Okay, right? It's always negative, right? You can upper bound by 0, so I drop it. Okay, and for sure, this is a positive term. This is a negative term. We want the summation to be negative. And the negative value, the upper bounds v dot, can be concluded as a negative definite, right? So we want it to be negative, but there's no any chance, right? So the best you can get is UUB. 能懂吗? Okay. Okay, good question. So based on this, where the only variable is x, you can compute the UUB for worst case. Okay. So maybe you have several questions why you don't do something, why you don't design VRF some other form that which might exist in your mind. But you can try. Somehow it doesn't work as you expected. Okay, like this. Okay, it doesn't work as you expected because there are some problems, some logic problems, and you have to do it. Go through all the process, then you will understand what the equation is. Okay, if you cannot find the logic errors, you can come to me. I will tell you why. Okay, so all this is a very systematic way to analyze the systems, to analyze the stability analysis. Let's go to the next topic. As you study more different analysis, it will become more clear why you want to do it this way. Okay, so next is high frequency. So again, the question basically is the same question. Given the nonlinear dynamics, okay, theta is unknown, constant, upper bound by absolute value of theta, upper bound by some positive constant. We want to design the control U and same structure, but the VR now here is different. We use a high frequency control. Okay, why it's called high frequency? So let me summarize as a side note here. We have mentioned high gain control, which is U design as minus kx minus k2x. Now it's high frequency control. And what's the controller? U equal to minus kx. The first one is the same. The second one is minus k2 sine x. Why it's called high frequency control? Because when you notice that if you plot out the sine function, then that's 1 and minus 1. Depend on you are on the right or left hand side, right? It's 1 or minus 1. And remember, the objective is to control x here, trying to control x to the origin, right? Means to around 0. And what happens when it's around 0? When around 0, it happens between 1 and minus 1 for sine x. When you are a little bit on the right hand side of 0, it's 1. Otherwise it's minus 1. So it switches between 1 and minus 1. Right? It switches between 1 and minus 1. So as it gets close to the origin, the frequency will change very rapidly. That's why it's called high frequency. And slightly more use a famous controller slightly more use this similar structure to do this. Okay, and there are advantages and disadvantages. Okay, advantage is it guarantee asymptotic stability, which means x will converge to 0. And the downside or the disadvantage is the high frequency in the control can damage your mechanical system, right? If your system is a motor and your control input is voltage, when you switch back and forth with a very high frequency, okay, on the voltage, which is the input to the motor will basically just oscillate around the basically it's stationary, just oscillate around a very small amplitude. It doesn't go anywhere, but it consumes energy and dissipate as a heat, right? So it's useless, okay? And the motor might damage because of the heat. So it's not. There are many improved versions of remote control. Anyway, but here we analyze what's the stability analysis here. So now we change VR to high frequency control, okay? And if you go back to here, high gain, there is no high frequency problems, right? When it goes from -1 to 1 or 0, the switch of the sign for this guy, okay, K2X, here is X, right? It depends on the switch. Basically is this, right? So it turns switch, it's continuous. Here is discontinuous, right? So when you substitute the control into the system, you got a closed loop dynamics here, okay? And remember, in the section we mentioned before that existence and uniqueness problems, what's the requirement for a solution to be exist in ODE? Remember? This is fx, right? Fx had to be what? Continuous. Is it continuous? No, it's not continuous. It's sign function here. It's not continuous. But so mathematically, solution doesn't exist. But physically, it exists because there's no sign function physically. Everything is continuous, right? You cannot switch physically with a infinite frequency, infinite high frequency, right? So mathematically, this is some problem with this dynamics, okay? But anyway, so let's do the analysis. V again design as the same as before, right? We take the time derivative so that we can substitute the dynamics x star here, okay? Coming from here. So now, again, you see the upper bound, okay, which is the first term, right? We put this with our absolute value, okay, and this absolute value is coming from this sine x times this x, right? 懂吗？ times x is equal to x, 对不对？对吧？ Sin x is this, right? And what's x? What's x? X is this. Right? And you multiply the two, it becomes this, right? So it's always positive. So the good news is because of the high frequency term, we can convert. Originally it was at K2X, right? In the high gain control is K2X. Now you leverage the high frequency term and you can now generate an absolute value. And that contribution is huge because now we can combine this x to absolute value of x with this absolute value of x, right? We can pull it out and merge these two, right? This is the upper bound of the constant, upper bound of the uncertainties. Now what you need to do is choose K2 large enough to dominate C, and this guy will always be positive, and this is always positive. So this second term will always be negative. So it's ND, and that's why this high frequency control can obtain asymptotic stability. I guess you already forgot what happened in high gain control when in the K2X term, right? Let me write down this term here. Upper bound by minus K2X, same as before, right? And minus K2 minus CX squared. Okay. Now, so just a minute ago, what happened in the high gain control? V dot is upper bound by minus K2 squared, which is the same minus K2X squared and CX. What's the difference? What's the difference? This is the same. This is same, right? The difference is this guy and this guy. Okay. Okay. And why? How did it come? Where did it come from? It comes from you apply high gain control, right? And in V, there's another X right before the bracket, right? And this X times this X becomes K2X squared, okay? And what happened here? We apply K2 sine X when it times another X right before the bracket, right? This X along and times this sine X create the absolute value of X and K2, right? So here's K2X squared, but here's K2 absolute value of X. That's the difference. And now you can put this into a bracket. In here, you cannot put it squared. Here's just absolute value of X. You cannot simply combine the two, right? So that's why you need to apply complete the square. Okay. And they pop out, they result in a positive constant. But here, there is no positive constant, right? As long as you guarantee K2 is greater than C, this is negative. And that is what you want, right? So it's ND, V dot is ND as long as K2 is greater than C. So high frequency ensures globally asymptotically stable as long as the gain is greater than the upper bound of the uncertainty. Okay. So conclusion, compare the two. Using high gain, you will get UUB, okay? Depending on whether the upper function is RU or not. And using high frequency, you can get exponentially stable or asymptotically stable. Eventually convert to 0. Same dynamic systems with unknown theta, unknown. And it's linearly parameterized, which means your unknown, your system parameter can be parameterized with unknown part, and the known part can be linearly separated. You can separate this linearly, okay? This is unknown, okay? This is known, given T is known. But what is non-linearly parameterized is X dot equal to, you put theta into the sine squared T, okay? Then is non-linearly parameterized or parameterizable, right? You can, how can you separate? Can you put theta times something that equal to this? No, right? But this, in this you can, right? Theta times sine T squared. Unknown and known. Unknown and known. But you cannot do this. That's the reason why this condition is required. You will understand in the next few slides. But before that, I have two questions for you. If theta here is known, now it's unknown, right? But if it's known, which controller will you design? Well, there are many controllers you can design, right? You can design feedback linearization controllers, which is this term times this term. Second term is for feedback, minus kx, right? And this term is just used to cancel nonlinearity in the dynamics. Then the closed loop dynamics become this, which is linearized. Second, if it's unknown, if theta is unknown, you cannot use this approach because it's unknown, right? You cannot implement something as a control, right? You cannot put something as unknown as a control, right? 懂吗? So everything on the right hand side in the control have to be known, okay? And that's the same motivation of adaptive control, okay? For unknown, we have introduced high gain, high frequency, and another one is adaptive control. In adaptive control, the structure is different, okay? We have minus kx before, and in high gain, we put minus k2x, right? High frequency, we put minus k2 sine x. And for adaptive, we put minus theta hat sine squared t. So here we have theta's hat. Hat is the estimate of this theta. Okay, so if you compare these two, it's very similar, right? This structure is similar, other than this theta hat replace this theta because theta is unknown, and I cannot implement something unknown. So I use the estimate of theta, which is called theta hat, and the estimate which means you need to design the dynamics to estimate this unknown constant, okay? So usually adaptive control comes with the control and the estimate of the parameters, okay? And they will be discussed later. So after you substitute the control into the dynamics, you get the closed loop dynamics here, okay? And this is the difference, the estimate error of theta, okay? And now we want to do the analysis, so you need this time. Remember this dynamics, and they will come into play in the neighborhood analysis. So now another question is, when you design the neighborhood function, this is the closed loop dynamics, okay? This is the closed loop dynamics, which is same as this. We just define theta tilde to replace the error, okay? Theta tilde to replace the error here, okay? So now we need to design the neighborhood function, okay? So which one will you pick? Option 1 or option 2? Option 1 is the one we used before for high gain, high frequency, okay? So which one will you pick? If you pick first one, even you say beta is negative definite, it's useless. Okay, it's useless. So I won't tell you why for now, but you will understand why later. So for now, we just use this one, okay? So we use this one to do the analysis, okay? So take the time derivative of this, okay, which you will obtain x times x dot theta tilde times theta tilde dot, okay， 就是对式均微分。Okay. So what is theta tilde dot? Theta tilde dot by definition is the time derivative of the difference, right? The two parameters, which is unknown, minus the time derivative of the estimate, okay? And because theta is a constant, unknown constant, so the time derivative will be 0. So this term will be equal to minus theta hat dot. Okay. So we need to design theta hat dot later. Okay. Let's just follow the analysis and see what's happening. So we expand this, it's an equal sign. So basically what we did is we just take the product, okay, minus k2 squares from here, and this term is from here, okay. And this term, we just replace tilde by hat dot. Okay, so here's a minus sign coming from here. We replace theta tilde dot by minus theta hat dot. Okay. So now you can design the adaptive law by this. The reason to design this is you can see this term can cancel out this term. Okay, right? You replace, you substitute theta hat dot from here into here, and these two terms will be cancelled. Now you have this. So it's ND or NSD. V dot is ND or NSD. If this is PD and you say this is ND, what the hell, right? 见鬼了，对不对？这也是 PD， 这也是 ND， 哎，那 theta 跑去哪里了 ？Right? You say it's PD, which depend on two parameters, two variables, x and theta hat. Here, the theta tilde disappears, right? So there's no way to say it's ND. If I write this, say this x, this is theta tilde, this is v, because v is defined as okay. So this PD, right? Now I say v dot. After a series of analysis, it becomes minus ks squared. This guy disappears. So it's ND or NSD. 这样懂了吗？这样懂了吗？以前我 so before I write this and I say x1 x2 squared, and if I got this is NSD. Now I just change x1 to x, x2 to theta tilde. NSD should remain NSD, right? 对吧？对吧？ I just change the notational variable, right? So it should be NSD, okay? What's the stability you can say here? According to the definition, we define theta tilde is the theta minus theta hat, and theta by definition is a constant. Okay, it is an unknown constant, which means theta dot will be 0. Okay, so when you take the time derivative, will be 0 minus theta hat dot. So what's the best you can conclude for the stability? Stable, right? Not asymptotically stable. If you use this to find the invariant set, you will say the invariant set is x equal to 0, right? But remember, v is a function of time and x, not just x. It also depends on time. So the invariant set, the concept we introduced invariant set is for autonomous systems. Okay, now it's non-autonomous systems. To prove that, so you cannot use that kind of invariant set theory. So the best you can try to further prove the stability. Okay, you can try to say this is globally asymptotically stable. okay, which is x goes to 0 by using Barbara's lemma. Okay. Barbara's lemma was not in the midterm 1, right? So I guess you haven't reviewed it yet. So basically, from here, we can say vita is equal to this, minus kx squared. And we want to find x will converge to 0. Okay, we use Barbara's lemma. So this give you what? Give you v will be bounded, right? 对吧? V dot is negative or 0. Worst case is 0. So what is v dot equal to 0? V is constant, right? So v will be bounded. It cannot increase, right? Given an initial condition v will either be a constant or a decrease, right? 对不对? So v dot equal to minus kx implies v is bounded, 对吧？有没有问题？有吗？有问题的点个头啊，画个图你就知道了。V, okay? If you say we start from here, given initial condition x, you can find the initial condition of v, right? According to this dynamics, equal to minus kx, right? So what's the worst case of minus kx? It never be positive, right? It's a non-positive stuff, right? So v cannot increase, 对不对? So given the initial condition, the worst case is v is bounded, or if you are lucky, it will decrease, 对吧? Which means what? In both cases means v is bounded. 这样有没有问题? Bounded means it doesn't go to infinity, 懂吗? Okay, so if v is bounded, that helps a lot. Okay, v is bounded means what? X, theta, tilde will be bounded because it's a PD function. 对不对? 我们现在 we want to go backwards from v, using v to investigate what's the property of x and theta tilde. Okay, so the best way to visualize this is using the 3D plots, x and theta tilde. Okay, we know v, this is v, right? V is bounded. It's PD, right? It's PD. And we say v is bounded. If initially v value is here, okay? This value won't increase, right? It only decrease or stay constant. It's bounded, right? Means the projection of this to this 2D plane will be the potential location for these two variables, right? Which means both have to be bounded, 对吧? These have to be bounded, these have to be bounded, because they are constrained in this area, right? Or mathematically, if this is bounded, from this structure, from this PD structure, both have to be bounded, 对不对? 你不可能说我一个 bounded 的东西，我可以让 variable 无限大，不可能嘛？有可能吗？找不到 right? You cannot find infinite large number of these variables and resulting in a bounded v value. That's impossible, right? So a bounded v implies both variables will be bounded. Okay, so it implies implies x is bounded. Theta tilde is bounded. If theta tilde is bounded, and this is constant, right? Constant is just a constant, so it had also be bounded. So these three variables will be bounded. Okay, 懂吗? And if these three variables is bounded, remember that the control will also be bounded, because control is what? Control is this. Control is this. And we say what is bounded? We say x, theta, tilde, theta hat are bounded, right? It's equal sign. This guy is bounded. This is bounded. X is bounded. So it must be bounded. 懂吗? It's equal sign. Bounded 会等于 bounded 的嘛，对吧？懂吗? So your control will be bounded. What does it mean if control is bounded? Okay, control is bounded is important. It means given this control structure, no matter, as long as your initial condition is bounded, you don't know the solution, but you know every solution, every trajectory will be safe. Your control input will be bounded. It doesn't require infinite, a very large control input to stabilize the system. 懂吗? 你不会说我设计一个控制器，它需要10000伏特的电压才能让马达稳定，不会。你这样设计的话，你有证明过了，这个会bounded，懂吗？你不会忽然间需要一个无穷大的力量才能让马达bounded，不会，懂吗？你的控制器就是bounded，懂吗？ So it doesn't require a large number of control input. No. So your hardware will be safe. Okay. So second, remember our objective is to prove x goes to 0. Okay. Asymptotically. So according to the closed loop dynamics, here, okay. Closed loop error system, which is x dot equal to theta tilde sine t squared minus kx. Okay, 也就是这一个 this one. After you substitute the control into the dynamics, you got the closed loop error system. Okay, so because this is bounded, okay, that your x dot will be bounded. 对不对? What does it mean if x dot is bounded? It means x is uniformly continuous. Okay, it means x is uniformly continuous. And the requirement to use Barbara's lemma is to show that x go to 0 is you have to be uniformly bounded and x had to be uniformly bounded and x had to be L2 function. L2 function means this. Okay, means the integral of x squared had to be bounded. And how to prove that is you can utilize this equation v dot equal to minus k x squared, and you integrate this. You integrate v dot, you integrate this. The tau equal to minus kx squared. The tau 0 to t, 0 to t. Okay. And this is v dot. This gives you vt minus v0 equal to what? Equal to this. Okay. And if you forgot what is L2 function, go back to review. But L2 function means this, the integral of a signal of x squared. Okay, x is a signal. If it's bounded, it's L2. Okay, so you need to check the left-hand side to see if it's bounded or not. And remember, we said V is bounded, right? V0 is here. Vt could be depend on what time, right? T here. This is Vt. So the difference of V0 to Vt is bounded, right? Because the largest value of V is V0. Smallest value of V is V0. So the largest difference is this, which is bounded. Right? So this difference is bounded, which means x is an L2 function. X is uniformly bounded. X is L2. So you can use Barbara's lemma to show x will go to 0 as t go to infinity. Every step here is required. Otherwise, you cannot go forward, right? So you need to exactly understand what's going on here, what is required for the next step, conclusions. 有没有问题? Maybe I'm running into, well, for the students who first see this won't feel comfortable, okay? It takes moments to absorb this. But as you go back, review again and again, you will feel comfortable because there is no new knowledge, right? Everything here, every theory we apply is it's based on your knowledge, right? You have learned this, okay? Nothing is new here, okay? I just taught you how to connect all these tools, how to use all the tools you have learned, okay? And the tools are not new. So conclusion is all signals include states, control input, and estimate errors are bounded. That's great, right? Control input are continuous. That's great. It's not high frequency, so it's safe to the mechanical systems. Control effort will be reduced. Why? Control effort this is compared to the robust control, because robust control, we don't know the system. System is unknown. We upper bound the system parameter by C, and as C is larger, we need to use a more powerful control input to the system to stabilize the system. And once you use adaptive control, which is this structure, theta hat, right? In the robust control, we just put a K2x, and this K2 have to be as large as you can, right? But here is theta hat. Theta hat is according to the estimate. Sometimes it will converge to the same parameters, right? If you are lucky, it converges to the same parameters. then you can save a lot of energy because you control a known model, right? If you are control an unknown model where you K2 had to pick a large value. So if you, I will give you a simulation as a homework. So you will see control and T. So given the same dynamics, if you apply you apply adaptive control. This is adaptive. Okay. And robust might be this. Okay. Might be this, robust or high gain. Okay. It uses a lot of energy compared to adaptive control because it doesn't know the system. It just uses the most reliable way, which requires a lot of energy. Okay, and the high frequency will be something like this, you know. High frequency along the way. Okay. Maybe it doesn't require that much control input, but frequency is always high. Okay. And the reason that you will oscillate is it trying to track some trajectory. Okay. Given a system, if you have an exact model knowledge, means you know what theta is, you can use feedback linearization, okay? Which reduce a lot of control effort because you know the system model, okay? Your control input reflects, you know when you need to use the minimal control input, okay? Because you know the model. So it reduces control effort, but it's not practical because it's usually unknown. Or sometimes the model is not, the parameter is not constant. Okay, when you drive a car, the mass is not constant, right? You have consumption on the petroleum, right? And the convergence proof. So it's not robust because if we have some disturbance like wind, like friction, which haven't been modeled in here, then when the disturbance exists, the stability is questionable. Okay, because you are control a systems, they are different from your model, right? So, and how about robust control, high gain control? High gain control, robust controllers includes high gain or high frequency, right? Because high gain can obtain a UV stability, high frequency can obtain a syntactic stability, and they are all robust to disturbances. Okay, right? Here we pick K2 as large as you can, as long as it's greater than the uncertainties, and same as here, right? So it's applicable to very broad class of systems. You can apply to, because it's robust, right? You can apply to, you don't have a exact model knowledge, right? You just put some tolerance. You can consider some tolerance in the system parameters. So you can apply to a broad class of systems. But one is stability, one is UV, one is exponentially stable. Okay, no one is the best, depending on what's your application. Okay. Adaptive control, usually this one is the best because, but the requirement is the system have been linear parameterizable. Okay, it can achieve a syntactic tracking or a syntactic stability, and the control energy is minimal. okay, compared to high gain control or high frequency control. Okay. And here is a summary of different controllers. Okay. So that's for today.